We are going entirely under the hood to decode the architecture that absolutely revolutionized modern AI. We are talking about transformers. And I should say revolution is not hyperbole. So by the end of our discussion today, the seemingly magical abilities of these modern AI models are going to make complete logical sense to you. Okay, let's unpack this. Because before we can understand the absolute genius of the transformer architecture, we really have to look at the flawed bottleneck system that came before it. The old guard of machine translation, exactly. Yeah, where does this story actually begin? So, the foundation of the story starts with the baseline architecture that completely dominated natural language processing, or NLP, before transformers took over the world. Okay. It's an architecture called the encoder-decoder model. You'll often see it referred to in the field as sequence-to-sequence, or simply CQ-SEC, sequence-to-sequence, meaning like taking a sequence of words in one language, say French, yeah, and outputting a sequence of words in another language, like English. Exactly, but I should point out it's not just translation. Yeah, many of the most complex NLP problems rely on pairs of sequences. Think about question answering, for example. Oh, right, like a chatbot. Exactly. The input sequence is the question, the output sequence is the answer. Or text summarization. The input is a 10-page article, and the output sequence is a one-paragraph summary. That makes sense. And crucially, a defining feature of these sequence pairs is that they're almost always of variable lengths. Right, because it's rarely a clean one-to-one word swap. Yeah. I mean, if you've ever tried to learn another language, you know this instinctively. Oh, totally. The English translation of a concept might take 5 words, while the original German might use a single massive compound word. Yes. And then the French might take 7 words. Yeah. You can't just swap words blindly. You really have to map the underlying meaning. Precisely. So the encoder-decoder architecture was specifically designed to handle this mismatch in length. It's essentially a two-part factory. Yeah, factory. The first part, the encoder component, takes that variable length input sequence, let's say a long French sentence, and essentially compresses it. It squishes it down. Exactly. Grinds it down, converting all those words and grammar rules into a single fixed length mathematical output state. Wow. Then it hands that fixed state over to the second part of the factory. The decoder component takes that compressed state, unpacks it, and converts it back into a brand new variable length output sequence in English. And there's a very important detail to notice in how the machine processes that sentence. Before the machine even looks at the first word, it uses special markers. Oh, the tokens. Right. It inserts a BOS token, which stands for beginning of sentence, at the very front, and an EOS token for end of sentence at the very back. Because, I mean, the computer doesn't intuitively know when a thought begins or ends, right? It doesn't see punctuation the way we do. No, not at all. It just sees a continuous stream of data. So it needs those guardrails. Exactly. It needs to know the boundaries of the specific data packet it is working with. So let's look at the landscape here. The machine learning world was stuck in a massive rut. They had this sequential sequence-to-sequence model that was agonizingly slow to train. It suffered from algorithmic amnesia where it forgot the beginnings of long sentences, and it funneled all its hard-earned knowledge into a tiny, suffocating bottleneck. It was a dark time for NLP. They desperately needed a way for the machine to somehow, look at the whole sentence at once without losing the context. They needed a paradigm shift. Absolutely. To solve this cutting-edge computer science problem, researchers didn't just look for better calculus. No, they didn't. They looked at human biology. What's fascinating here is how the literature introduces the concept of the attention mechanism. Yes, this part blew my mind. Before showing us a single line of code, before throwing any matrices at the wall, the researchers take us on a detour into the realm of human psychology and the staggering biology of the optic nerve. The research points out that the human optic nerve receives information on the order of 1 billion bits per second. 1 billion bits. Every single second. That is vastly incomprehensibly more data than the human brain has the actual capacity to process and analyze in real time. If our brains attempted to process every single photon of light, every shadow, every blade of grass, and every piece of sensory data sequentially and with equal computational weight, we'd freeze. We would be completely paralyzed, our cognitive systems would crash. So over millions of years, biological evolution developed a brilliant filtering system to keep us alive. Visual attention. The literature actually brings in William James to explain this. Yes, for those who don't know, William James is widely considered the father of American psychology, writing way back in the late 19th century. A true pioneer. He created a 2-component framework for how human attention actually functions in the real world. And understanding this 19th century psychology is absolutely crucial for understanding the 21st century AI that comes later. Can you break down James's framework for us? Certainly. So, William James theorized that the spotlight of human attention uses two distinct, separate types of cues to bias our sensory input and decide what is important enough to process. Okay. The first type are non-volitional cues, or involuntary cues. These are strictly based on the saliency and noticeability of targets in your environment. The text gives a great example of this. Imagine you are sitting in a busy, noisy restaurant, trying to drink your coffee. Suddenly, a baby at the next table starts screaming at the top of its lungs. Right. Or someone drops a tray of brightly colored plates that shatter on the floor. You don't consciously choose to pay attention to the screaming baby or the crashing plates. Your brain is involuntarily, forcefully pulled toward those events. They are highly salient, they demand attention. Exactly, your biological alarms go off. The second type of cue, however, is volitional or voluntary. This is based on a subject's deliberate, conscious, and goal-directed effort to focus on a specific target. So an active choice. Yes. The literature gives the example of scanning a dense page of text specifically to find the answer to a trivia question. You aren't just reading passively, you are actively, voluntarily searching for a specific pattern. Okay, so we have these two forces. Involuntary cues pulling our attention toward bright and loud things, and voluntary cues directing our attention toward our specific goals. Exactly. This makes perfect sense for human brains. But how on earth bridge the gap between William James's 19th century observations and modern deep learning algorithms? It does it by taking those psychological concepts and mapping them directly onto the variables used in the attention mechanism algorithm. Oh wow. It creates a mathematical analogy. The research states that in deep learning, those deliberate, voluntary, goal-directed cues map to what the AI architecture calls queries. Queries, got it, that's the active search. Precisely. The involuntary, highly noticeable cues in the environment map to what we call keys. Keys, okay. And the raw sensory inputs themselves, the actual data you want to consume, map to values. Okay, let me try to construct a physical analogy for you listening. To really ground these three abstract terms, query, key, and value. Because this trio is the engine of everything that follows. It really is. Think of this like walking into a massive, sprawling public library. You, the patron, walk in with a specific intent in your mind. You want a book on how to bake sourdough bread. A noble goal. That intention in your head, that specific goal, is the query. It's your voluntary, volitional focus. Right, it's what you are actively looking for. Now you look around this massive library. You obviously don't pull out every single book and read it sequentially left to right to find the bread recipe. No, that would be the RNN method. Exactly. Instead, you look at the large signs posted at the ends of the aisles. History, science, culinary arts, fiction. Those signs are the keys. They are the involuntary, highly noticeable labels that the environment is explicitly presenting to you to grab your attention and tell you what information is stored there. And what happens in your brain when your query interacts with those keys? Well, your mental query of baking bread heavily matches the key labeled culinary arts. The words align conceptually. So you direct your physical attention down that specific aisle, completely ignoring the history and science aisles. You filter out the noise. Finally, you walk down the culinary aisle and pull the actual physical books off the shelf. Those books, the actual pages and text you consume, are the values. That is exactly beautifully how the attention mechanism in a neural network operates. It's a great metaphor. The literature describes the system as a memory bank constructed of keys and values. When the neural network is queried, when it asks, what do I need right now? It generates an output based on the specific values whose keys best map to that specific query. It is selectively focusing on highly relevant elements of the data while mathematically filtering out the less relevant noise, exactly mimicking the biological trick of the human brain. A silicon computer chip doesn't have biological instincts. No, it doesn't. It doesn't have a gut feeling about which aisle to walk down. The machine needs hard, rigorous, executable math to actually measure the similarity between a query and a key in order to select the right values. It does. How do we turn that library trip into calculus? Yes, the metaphor has to become mechanics. This brings us to the formalization of the attention layer. Okay, brace yourselves for the math. It's not too bad, I promise. The material defines the memory unit as consisting of pairs of keys and values. The attention layer receives an input query, and it needs to return an output. To do that, it has to score the similarity. It has to ask mathematically, How much does my query look like this particular key? Exactly. The researchers introduce a score function to evaluate the query and a specific key to generate a normalized score. There are several ways to calculate this score, but the researchers highlight one method as being incredibly elegant, simple, and highly efficient for computers. And what is that? The dot product. Here's where it gets really interesting. I know the phrase dot product brings back terrifying memories of high school linear algebra for some of you listening, but how does it actually calculate that score in a way we can visualize? The dot product is a fundamental algebraic operation, but physically it's just a way to measure how well two vectors align in space. Vectors being the arrows. Right. Remember, our words have been turned into vectors arrows pointing in multidimensional space. To get the dot product, you multiply the corresponding elements of the query vector and the key vector and sum them all up. So without getting bogged down in the actual numbers, what does the result mean? It's a measure of directional alignment. If the query arrow and the key arrow are pointing in roughly the same direction, meaning the concepts are highly related, like bread and baking, their dot product will be a high positive number. And attention. Yes, the machine should focus here. But if they are pointing in completely perpendicular orthogonal directions, meaning they have nothing to do with each other, like bread and quantum physics, the dot product is 0. So no attention. Ignore it. Exactly. It's brilliant because it has no extra parameters to tune. It's not guessing, it's just using raw absolute geometry to see if concepts overlap. That's incredibly elegant. There's always a catch. The literature points out a massive technical hurdle with relying on the simple dot product. As we build bigger and bigger AI models, as the dimensions of our data increase to capture more nuance, these dot products start causing serious problems. This is a critical engineering detail recognized by the researchers, a team led by Ashish Vaswani, right? Yes. Let's say your query and key vectors are highly detailed, meaning they have a dimension depth of 512. Okay, when you multiply 512 values together and sum them up, the resulting mathematical score can be a staggeringly huge number. Okay, but computers love big numbers. Why is a huge score bad? Because of the bottleneck of the very next step in the pipeline. Oh, right. The network doesn't use those raw, massive scores directly. It takes those scores and passes them through something called a softmax function. Softmax. Let's explain softmax. I like to think of softmax as a mathematical winner-takes-all percentage calculator. That's a good way to describe it. It takes a bunch of raw scores and squishes them down so they all add up to exactly 1.0, or 100%. If one score is slightly higher than the others, softmax aggressively amplifies it so it becomes 90% and crushes the others down to 1% or 2%. It turns raw scores into clean probabilities. That is exactly what it does, and it achieves that squishing by using exponentiation. And here is the fatal flaw. Okay. If you feed massive, huge numbers into an exponential softmax function, the math gets pushed into extreme regions. The resulting curve becomes almost entirely flat. And when a mathematical curve becomes flat, its slope is 0. Yes, and if we remember our blindfolded hiker from earlier. Exactly. We are right back to the vanishing gradient problem. The slope is 0, the network stops learning, the model gets completely stuck because the numbers got too big. Wow. So the geometry of the dot product works perfectly, but the sheer size of the numbers breaks the learning process. How did Vaswani's team fix this? Vaswani proposed a brilliant but incredibly simple fix called the scaled dot product. It's almost shockingly simple. I love simple fixes. You take that massive dot product score and you simply divide it by the square root of the dimension size. Wait, really? You just divide it to shrink it back down? That's it. If your dimension is 512, you divide the score by the square root of 512. Unbelievable. That scales the numbers back down into a manageable, constrained range. It keeps the softmax function right in the sweet spot where the gradients are steep, the slopes are clear, and the model can learn efficiently and rapidly. The researchers actually note that while other attention methods exist, like additive attention, which uses complex hidden layers and extra learned weights, this scaled dot product is vastly faster and much more memory efficient for modern hardware. It's a sleek aerodynamic calculation, highly efficient. Okay, so we have the math. We know how to score a query against a key to pull the right value. How did researchers originally integrate this beautiful attention mechanism into that old, flawed sequence-to-sequence model we talked about earlier, the one with the terrible bottleneck? This was the first major breakthrough. Instead of passing just one compressed context vector to the decoder, the attention mechanism was used to physically connect the decoder directly to every single output state of the encoder. It shatters the bottleneck entirely. It does. The straw is gone. The pipeline is blasted wide open. Exactly. In this setup, the outputs of the encoder's hidden states, the mathematical representations of every single French word in our sentence, become the keys and the values. Okay. They are the library signs and the books sitting on the shelves waiting to be accessed. And where does the query come from? The query comes from the decoder side. Specifically, it uses the output of the previous decoder state. Let's walk through a specific example for you listening to make this concrete. We are back to translating j'aime le thé to I love tea. Right. Let's imagine the translation is underway and the decoder just successfully generated the English word love. That word love and its underlying mathematical hidden state flows into the attention layer and acts as the query. It's the patron walking up to the librarian and saying, I just read the word love. What should I read next to finish this thought? Yes. The attention layer takes that query for love and calculates a scaled dot product score against every single key sitting in the French encoder. It scores j'aime, it scores la, it scores they. It evaluates the entire source sentence all at once. It doesn't rely on a compressed memory. It looks directly at the source material. And through that softmax function we discussed, the math figures out that based on the fact that we just generated the concept of love, the highest attention weight, the strongest geometrical alignment, should be placed squarely on the key for the French word fait. And because it focuses its mathematical attention heavily on the key for they, it pulls the corresponding value and the decoder spits out the English translation T. The bottleneck is dead. At any given time step, the decoder has the power to look back across the entire expanse of the source sentence and surgically pull exactly the specific context it needs, regardless of how long the sentence is. This is like a monumental victory. We completely fixed the information loss. The AI can finally remember the beginning of the sentence. It was a massive win. But as I am looking at the timeline of the research, there's a catch here, isn't there? Yes, there is a massive lingering catch. Let me guess. The model is still using RNNs at its core engine. You got it. The encoder is still calculating the hidden state of word 3 based on word 2. Which means the encoder still has to read j'aime, wait for the calculation, wait for the calculation. It is still strictly painfully sequential. And therefore, it is still fundamentally too slow to train on massive datasets. Right. The attention mechanism was a massive leap forward for the accuracy of translation, but it did absolutely nothing to solve the computation speed problem. It's still a one-lane highway. Exactly. To train on the terabytes and petabytes of text data required to build true, modern AI, the machine learning world needed a revolution. They couldn't just add a room to the house, they needed to tear the house down to the foundation. Which brings us to the absolute core and the architectural game changer that defined a generation of AI, Vaswani's transformer architecture. In a landmark paper, Vaswani and his team proposed an architecture that truly shocked the field. I bet. Their solution to the slow, sequential bottleneck of the RNNs. They simply got rid of the RNN entirely. Just toss it in the trash. Decades of NLT architecture, gone. Completely scrapped it. Wow. Instead, they looked over at a different field entirely. Computer vision, they looked at convolutional neural networks, or CNNs, which are typically used for processing images. Okay, CNNs. CNNs are incredibly fast because they can calculate thousands of pixels in parallel, all at the exact same time. Vaswani's team wanted to steal that massive parallelization power and combine it with the attention mechanism to capture long-range sequences in text. Okay, I'm gonna play devil's advocate here. Go for it. Because if I am a linguist, this sounds literally impossible. The entire point, the fundamental bedrock of human language is order, time, sequence. Absolutely. If I say the dog bites the man, that is a tragic, sad event. If I use the exact same vocabulary but say the man bites the dog, that is bizarre headline news. Right, the meaning flips entirely. The order of the words dictates the meaning. If you throw away the sequential RNN and you process all those words at the exact same time in parallel, how on earth does a machine know the order? To a parallel system, isn't a sentence just a scrambled bag of loose words? Since the recurrent network wasn't there anymore to implicitly track the passage of time step by step, they had to explicitly, forcefully inject the concept of word order into the math of the model. They had to physically stamp each word with a time code before throwing it into the parallel processor. Essentially, yes. This brilliant technique is known as positional encoding. The researchers laid out strict requirements for this timestamp. It needs to generate a unique value for every single position in a sentence. The distance between positions needs to be mathematically consistent, whether it's a 5-word sentence or a 50-word sentence. Exactly. It needs to be deterministic, meaning it calculates the same way every time. And crucially, it needs to generalize to sentences longer than anything the model ever saw during training. So the engineering question is, how do you build a timestamp that meets all those rules? The literature points out that one trivial, obvious way to accomplish this is just to use basic binary representation, right? Counting in zeros and ones. Position 1 is encoded as 001, position 2 is 0101, position 3 is 011. It's unique, it's consistent. Problem solved, right? Not quite. The researchers dismissed this binary approach very quickly. Why? Because using binary values is incredibly costly from a memory perspective. Remember, our embedding dimensions are often 512 deep. Okay. If you try to use a 512 dimension binary matrix to encode the position of words in a long 1,000-word document, you create a massively inefficient, sparse matrix filled with mostly empty zeros. It wastes too much memory. So if counting in binary is out, what did they use to stamp the time? They turned to continuous mathematics. They used trigonometry. Specifically sine and cosine functions. Trigonometry. Sine and cosine waves. I thought we were trying to translate French poetry, not map the ocean tides or calculate the trajectory of a pendulum. It sounds wild, I know. How does a continuous wave tell a computer where the word dog is in a sentence? This sounds like a magic trick. Can you explain the mechanics of this without reading the formulas? It does sound like magic, but let's visualize it physically. Instead of thinking about waves, think about a combination lock, or the hands of a clock. Okay, a clock. Imagine a clock with not just 3 hands, but 512 hands, representing our 512 dimensions. Okay, a massive complex clock. The first hand on this clock spins incredibly fast, like the second hand on steroids. Got it. The next hand spins a little slower, the next one even slower. By the time you get to the 512th hand, it is moving so slowly it takes years to make a single rotation. Oh, would you? What Viswani's trigonometric functions do is freeze time at a specific moment. For position 1, word number 1, you look at the clock. The fast hand is pointing at 12. The slow hands haven't moved. That specific arrangement of the 512 hands is a unique numerical fingerprint. I see. For position 2, word number 2, you look again. The fast hand has spun rapidly to a new spot, the middle hands shifted slightly, the slow hands barely moved. That is an entirely new, completely unique fingerprint. Because you have a mix of rapidly changing values, the high-frequency sine waves, and incredibly stable slow-changing values, the low-frequency waves. Every single position in the sentence gets a completely unique, unrepeatable signature of numbers. Exactly. It's a continuous, smooth mathematical representation of time and order. You nailed it. The researchers generated this positional matrix, and what does the transformer do with it? What does it do? It simply adds it. It literally takes the mathematical matrix representing the word meaning and adds it to the trigonometric matrix representing the position. So the word dog isn't just the raw concept of dog anymore. It's mathematically fused into dog at position 1. Yes, and the word man becomes man at position 4. And because they have those permanent timestamps baked into their core identity, the model can now process the entire sentence all at once, in parallel, without ever losing track of the sequence. It regains the blistering speed of parallel computation without losing the crucial meaning-defining information of sequence and order. It is an astonishingly elegant solution. So what does this all mean for the architecture? We have the words, we have explicitly injected their physical positions using trigonometric clock hands, and we have successfully thrown the slow RNN in the garbage. We have. But how does the transformer actually read this massive parallel data to understand the context? If it's not reading left to right, what is it actually doing? It is looking everywhere, at every word, all at the exact same time. Everywhere at once. Yes, using a mechanism called self-attention. Attention. Yeah. How is this different from the regular attention we discussed earlier with the encoder looking at the decoder? In the earlier model, the decoder was querying the encoder. The English output was looking at the French input. In self-attention, a sentence looks strictly at itself. Yes. Each input vector, let's say a single word in our French sentence, goes into the layer and mathematically generates its very own query, key, and value. All 3 components come from the exact same word. Yes. The network learns 3 different weight matrices. It multiplies the input word by these matrices to project it into 3 different roles. So the single word le in our sentence splits into 3 avatars. It generates a query to ask the rest of the sentence, what other words conceptually relate to me? Exactly. It generates a key to declare to the rest of the sentence, here is the specific grammatical role I play. And it generates a value, which is its actual underlying meaning. You've got it. And then the true magic of parallelization happens. Every single word's query is dot product scored against every other word's key in the exact same sentence simultaneously. Whoa. J'aime attends to le and thea. They attends back to j'aime and le. They all talk to each other. They'll score each other in one massive, instantaneous matrix calculation. It's building a massive interconnected web of internal context. It's instantly figuring out that they is the direct object of the affectionate j'aime, regardless of how many adjectives or filler words might separate them in the text. And it's doing it all in parallel. But Vaswani's team didn't stop there. Of course not. One layer of self-attention is powerful, but human language is incredibly dense. A single word can have multiple meanings depending on tone, grammar, and historical context. The research explains that instead of using just one single attention mechanism, they implemented something called multi-head attention. Multi-head. Like a hydra. Very much like a hydra. The literature mentions they originally used 8 parallel heads in their foundational model. Why 8? Isn't one massive web of context enough to figure out a sentence? Not for the deep complexities of language. The researchers noted that multi-head attention provides different subspace representation. Subspace representation? This is a technical way of saying it allows the model to capture completely different aspects or layers of meaning from the exact same input. Let me try another analogy here to visualize these 8 heads. Imagine I write a novel, and I hand the manuscript to a single solitary editor. That one editor is tasked with checking the spelling, ensuring the emotional tone of the characters is consistent, verifying the historical accuracy of the setting, and checking the pacing of the plot, all by themselves, on a single read-through. They are absolutely going to miss things. They're trying to hold too many conflicting perspectives in their head at once. They are doing too much with one pass. Exactly. But what if, instead, I hire a team of 8 highly specialized editors, and I hand them all a copy of the manuscript at the same time? That changes things. Editor 1 is the grammar nerd. They only look at subject-verb agreement. Editor 2 is the empath. They only crack the emotional arc of the protagonist. Editor 3 is the historian. They only look at geographical descriptions. They each read the exact same text. But because their internal priorities are tuned differently, they pull totally different contextual clues from the words. That is precisely what the attention heads are doing in the neural network. Each head is initialized with its own uniquely learned set of weight matrices. Oh, wow. Over millions of training cycles, one head might naturally specialize entirely on learning grammar, another on tracking verb tense, another on identifying pronouns. They each calculate their own independent context matrix. And then what? How do the 8 editors consolidate their notes so the machine can make a final decision? The mechanism is wonderfully simple. The outputs from each of the 8 heads are simply concatenated, meaning stitched together. Stitched together side by side into one massive matrix, and then multiplied by one final overarching weight matrix. This generates a single, unified output matrix that contains the combined, incredibly rich, multi-layered contextual insights of all 8 specialized heads. It is brilliant. So that is the encoder side. It reads the French sentence with 8 parallel heads, mapping every possible relationship and nuance instantly. But what about the decoder side? How does it actually generate the English text without an RNN? The decoder uses a very similar multi-head attention structure, but with a critical foundational alteration. The researchers call it masked multi-head attention. Masked, meaning we are intentionally hiding something from the machine. Yes. Remember how a model trains? During training, we feed the decoder the correct, finished English translation so it can calculate its error and learn. But we can't let the model peek at the future words before it actually predicts them. Right. If it is currently trying to predict the word tea, it shouldn't be allowed to look ahead in the training data and see the word tea, because then it wouldn't actually be learning the rules of translation. It would just be cheating. It would just copy the answer key. So how do they mathematically blindfold the model to the future? They apply a masking weight matrix. The literature specifies that this mask matrix forces any future tokens to be represented by negative infinity, while previous tokens are left alone. Wait, negative infinity? That's not just a small number, that's the absolute abyss of math. Why not just use 0? Why do we have to go to negative infinity? It comes back to the softmax function we discussed earlier. The percentage calculator. Exactly. If you try to hide a word by making it score 0, softmax will still assign it a small non-zero probability because 0 is still a valid mathematical value on the curve. See. To force the exponential softmax function to output an absolute, dead, unrecoverable 0% probability, you have to push the input value all the way down into the abyss of negative infinity. That's intense. When softmax sees negative infinity, it flattens it to true 0. The model is mathematically fundamentally blinded to any word that comes sequentially after the one it's currently processing. It literally cannot see the future. Wow. That is hardcore math solving the logical problem perfectly. Yeah. And as we zoom out in this architecture, the literature also mentions briefly that throughout this entire transformer sandwich between the multi-head attention layers and the feed-forward networks, there are two other critical stabilization techniques. Yes. Residual connections and layer normalization. Yes, often referred to in the diagrams as the add and norm step. The inputs are physically short-circuited around the attention layer and added directly to the output. Like a bypass. Exactly. This is a technique heavily borrowed from deep image processing networks like ResNets. It ensures that the original raw input signal, the pure identity of the word, isn't totally degraded or lost as it passes through layer after layer of complex mathematical transformations. It's like keeping a backup copy of the raw data, just in case the editing process went too far. And what about layer normalization? The text has some complex equations for this, but what is it physically doing? If we want to use an accessible analogy, layer normalization is essentially an automatic volume knob for the neural network. A volume knob. As data passes through these millions of parameters, sometimes one specific layer might output incredibly huge numbers. It starts screaming. If it passes those screaming numbers to the next layer, it blows out the math. Layer normalization mathematically forces the outputs of each layer to center back around a mean of 0 with a standard variance. It automatically turns down the volume of the screaming layers and turns up the volume of the quiet layers, so the next part of the network receives a clean, conversational, standardized signal. Exactly. The researchers note that this reduces something called covariance shift. Covariance shift? It just means the hidden layers don't have to constantly panic and readjust their weights to handle wild, unpredictable swings in the volume of the data passing through them. It keeps the math incredibly stable. Okay, stability of speed. Yes, it speeds up convergence, meaning the model learns much, much faster, and it makes the model less dependent on the size of the data batches it is trained on. Okay, let's take a breath. We have unpacked the theory, we have explored the mechanics, we have 8 heads of parallel attention acting as specialized editors, we have trigonometric positional clock hands injecting time, and we have masked decoders blinded by negative infinity. It's a lot. It sounds like absolute science fiction compared to the slow, amnesiac RNN we started with, but theory is just theory. The real question is, does this massive, complex transformer actually work better in the real world? The researchers set up an ultimate showdown, a real-world, highly empirical case study directly comparing the pinnacle of the old RNN architecture against the new Vaswani transformer. The arena for this showdown is machine translation, specifically translating English sentences into French. Tell us about the data they fed these models for this test. They used a well-known parallel corpus, a huge dataset of matched sentences from a linguistic site called manythings.org. The researchers are very transparent with their statistics. They started with 135,842 language pairs. That's a lot of data. It is, but they filtered out sentences that were anomalously long, cleaning the dataset down to a highly focused 131,951 pairs. And they split this data up just like a standard or rigorous machine learning experiment. Yes, 80% of the data was used purely for training the models. 10% was used for validation, which is like giving the model a practice quiz during training to see how it's doing. And the final 10% was held completely back, locked in a vault, to be used as a blind test set at the very end. They didn't just dump the data in, they looked at the shape of it. Why is that important? Data cleaning and exploration is arguably 80% of a data scientist's job. If you feed garbage into a model, you get garbage out. Sure. They generated distribution plots that showed the vast majority of the sentences in this specific dataset were relatively short, between 4 and 8 tokens long. They also examined the top 20 most frequent words. Right, and for the most part, it's exactly what you'd expect. The English word the, mapped heavily to the French le or la, is mapped to est. But the analysis caught a really fascinating quirk introduced by the tokenizer they used, a popular software library called Spacey. Yes, when they looked at the frequency list, the word dawn showed up incredibly high on the English side. Dawn. Like a mafia boss. Why are there so many mafia bosses in this French translation dataset? Exactly the kind of question Edie is meant to provoke. As the researchers noted, it wasn't mafia slang, it was a quirk of how the tokenizer handled punctuation. It took the English contraction don't, and instead of keeping it as one concept, it aggressively split it into dawn and an isolated apostrophe T. Why does a tiny punctuation split matter so much? Because if you don't catch that during your analysis, your AI model is going to spend millions of compute cycles desperately trying to learn the deep semantic meaning of the standalone word dawn, when in reality it's just a broken fragment of a contraction. Oh, that makes total sense. By analyzing the data iteratively, you catch these pre-processing quirks, you fix them, and you vastly improve the final model results. Okay, so the data is clean, the quirks are noted. Let's introduce the contenders for the showdown. Contender number 1 is the Bottleneck attention model. This represents the absolute pinnacle, the final, most optimized form of the old guard. It uses a bidirectional gated recurrent unit, or GRU, which is an advanced type of RNN. Bidirectional meaning it tries to cheat the sequential problem by reading the sentence left to right and then reading it again right to left and smashing the results together. Exactly, it had an embedding dimension of 256, and importantly, it used a dropout rate of 0.15 for regularization. Let's explain dropout, because I love this concept. Wait, you are telling me they intentionally, randomly turn off 15% of the neural network's brain during training? Yes, they do. That sounds like giving the AI a lobotomy. Why would you cripple your own model? It sounds counterintuitive, but it's a brilliant way to prevent something called overfitting. Think of it like a classroom of students studying for a final exam. Okay. If you let them study with the exact answer key every day, they won't actually learn the concepts, they will just flawlessly memorize the answers. Dropout is like forcing the students to study without their notes or constantly changing their study group. Oh, I get it. By randomly turning off 15% of the neurons during every training pass, the network cannot rely on any single dominant pathway to memorize the data. It forces the network to distribute its learning, making it much more robust and generalized when it faces data it has never seen before. It forces it to learn the actual rules of French, rather than just memorizing the flashcards. Okay, so that is the heavily optimized RNN. Who is contender number 2? Contender 2 is the PyTorch transformer model, built entirely on Smarty's architecture. It features 256 dimensions, those 8 multi-headed attention editors we discussed, 6 full layers for both the encoder and decoder, and a massive feed-forward network dimension. The stage is set, the data is loaded. They train both models on the 80% training data for dozens of epochs. They test them on the 10% blind test set. I am enthusiastically asking for the final score. Who wins the machine translation heavyweight belt? The researchers provide the hard empirical metrics, looking at both cross-entropy loss and a vital metric called perplexity. Let's briefly explain perplexity for the listener, because it's the gold standard for evaluating language models. Think of perplexity as a literal measure of how confused or surprised an AI model is by actual human text. Yeah, if a model has high perplexity, it means when it looks at a human sentence, it is constantly surprised by the next word. It is essentially guessing randomly. If I say, I am going to bake a loaf of, a highly perplexed model might guess shoes because it has no idea. It's confused. A model with low perplexity is highly confident and accurate. It knows the next word is probably bread. So lower perplexity is vastly better. What happened with the bottleneck RNN model? Looking at the performance charts, the validation loss for the RNN drops initially as it learns the basics, but then it hits a hard wall. It plateaus. And crucially, around epoch 14 of training, the validation loss completely stops improving, even while the training loss keeps going down, which indicates it started overfitting. Despite the dropout, it hit the limit of its architecture. It started just memorizing the training data and lost the ability to generalize to new French sentences. Exactly, it maxed out its potential. Now look at the transformer. The validation loss doesn't hit that wall, it plummets, dropping significantly further than the RNN. And it never shows that massive divergent split between training and validation loss. It remains incredibly stable and continuously learns. And the final, ultimate perplexity score on the blind test set. Yeah, the data it had never seen before. It is a decisive absolute victory. The highly optimized RNN achieved a perplexity score of roughly 12. The transformer achieves a perplexity score of less than 6. The transformer's perplexity was almost 3 times less than the RNNs. Incredible, isn't it? It was mathematically, demonstrably 3 times less confused by human language. It understands the underlying structure vastly better. It is a total knockout. But if we connect this to the bigger picture, winning a math contest and plotting perplexity curves on a graph is great for researchers writing papers. As users of this technology, we don't just want to see the numbers, we want to see why the transformer is smarter. Right. We want to open the black box. We want to see the machine actually thinking. But how do you do that? It's just billions of weights, matrices, and byproducts inside a silicon chip. You can't just ask it how it feels. You can't ask it, but you can track its footprints. The researchers detail a fascinating explainability method called gradient tracing. Walk us through gradient tracing. How does that peer into the AI's brain? You perform a forward pass, meaning you run the input sentence through the model normally to get a translated word. You isolate the output token with the highest probability, the final choice the machine made. Then you perform a backward pass from that specific generated word. You mathematically trace the electrical signal, the gradients, backwards through the entire network, all the way back to the original embedded input words. You are tracing the electrical current backward to see exactly which input words lit up the brightest when the machine made its final decision. Exactly. This populates a matrix of weights that we can visualize as a heat map, commonly called an attention map. Let's paint a picture of them for the listener. In one example, the model is translating the French phrase "je vais l'eau" to English. Yes, when the machine finally outputs the English word going, the attention map shows a massive glowing red concentration of gradient heat directly over 2 specific French words. It was looking intensely at the words je and vais. It mathematically understood that the complex combination of those 2 specific words mapped perfectly to the English concept of going. And in another example, when it generates the English word library, the attention map shows almost 0 heat on the surrounding words, but a massive spike of heat directly on the French word bibliothèque. The web of context that the multi-head attention built is literally physically visible in the heat map. But the real visceral proof of the transformer's superiority is when the researchers put the RNN and the transformer head-to-head on specific grammatically tricky sentences to see exactly why the RNN failed and the transformer succeeded. Oh, I love these examples. The literature highlights 2 brutal, revealing examples. Yes, this is where the bottleneck becomes painfully obvious. The first input sentence is the English question. How long will you be here? The old sequence-to-sequence RNN attempts to translate this into French. Its final output is Combien de temps serais-tu ici? Any fluent French speaker listening will immediately cringe at that sentence. It is grammatically broken. Right. The RNN incorrectly paired the verb serait, which is strictly the formal or plural conjugation, with the pronoun tu, which is strictly the informal singular pronoun. It's like saying, how long will thou be used here? It just clashes. But why? Why did a multi-million-dollar AI make such a basic first-year language student error? Because of the bottleneck. By the time the sequential RNN painfully crawled all the way to the word here at the end of the English sentence, its compressed single-vector memory had completely diluted and forgotten the precise grammatical constraints established at the very beginning of the sentence. Forgot the start. It knew it needed a verb, and it knew it needed a pronoun, so it just guessed one of each based on loose probability, but it lacked the cohesive memory to mathematically sync them together. It lost the thread. Now look at the transformer's output for the exact same input sentence. Combien de temps seras-tu ici? Seras-tu. It perfectly, flawlessly matched the informal singular verb conjugation with the informal singular pronoun. And it didn't do it by memorizing the phrase. It did it because it wasn't relying on a choked, compressed memory. Through its 8 heads of parallel self-attention, it was looking at the words you and be simultaneously, calculating their geometric dot product alignment, and explicitly establishing the precise grammatical link regardless of how many words separated them. The second example provided is even more stark, and it shows the ultimate failure of the old AI. The English input sentence is, "It is snowing at my house." The RNN grinds through this sentence, and its final French output is "C'est à la maison," which, if you translate that back to English, literally just means "it is the house." It completely, utterly dropped the core concept of the entire sentence. The foundational idea of the weather snowing vanished entirely into the bottleneck. It got lost in translation, literally and mathematically. The RNN was so obsessed with the sequential end of the sentence, my house, that it overwrote the beginning. But the transformer, It was flawless. Ineshimwa. Not only did it flawlessly retain and translate il neige, meaning it is snowing, but it also gracefully captured the natural contextual idiom chinois for my house instead of a rigid, literal word swap. My mind is honestly blown by this, because what we are clearly seeing in these glowing gradient maps and these perfect translations is that the transformer didn't just become a faster dictionary. Not at all. By ditching the agonizing sequential crawl, by using specialized parallel heads to look at all the words at once, by stamping them with trigonometric position waves so it never loses its place, it actually grasped the context, the intent, and the grammar of the whole thought. It finally learned how to pay attention. Let's recap this massive architectural shift for you listening. We started in the murky, agonizingly slow world of the old sequence-to-sequence models. We saw the fatal limiting flaw of the RNN. The bottleneck. The bottleneck. It has forced entire complex sentences into a single mathematical vector, crushing the data, losing information, suffering from vanishing gradients, and utterly failing to connect long-distance concepts. Then when the math failed, the field looked to biology. We explored William James's 19th century psychological framework of visual attention, how human brains use involuntary keys and voluntary queries to survive a flood of sensory data. Brilliant. The researchers brilliantly translated that biological instinct into hard calculus. Queries, keys, and values scored by scaled dot products to measure geometric alignment. And finally, Vaswani's massive, paradigm-shattering breakthrough, throwing away the sequential RNN entirely, unleashing the blistering parallel processing power of the transformer architecture, using spinning sine and cosine waves to explicitly encode the physical position of words. And multi-head self-attention. Yes, multi-head self-attention, a team of specialized mathematical editors, to build a rich, multi-layered web of context across an entire sentence simultaneously. And as the rigorous data proved, it completely crushed the old models in perplexity, accuracy, and sheer fluency.